Okay, so now we're going to take a look at some computations with this notion of limits and infinity. The big idea, the big theorem we have here is this: the limit as x goes to infinity of c. C may be any specific constant value. This may be any constant. And we have over x raised to the r power. So a specific instance of this might be limit x goes to infinity of maybe 5 over x to the third. R is 3, c is 5. So this is a specific occurrence of this idea. There's no, now what we do require is that r must be greater than 0. If r is less than 0, then we're moving this up to the numerator. It's a different notion. The limits at infinity, not always, but usually tend to get a little more interesting as the functions we're working with involve fractions. So let's assume that r is bigger than 0. We have c divided by x to the r, limit x goes to infinity of that function. Here's this one specific case. Another case might be limit x goes to infinity of negative 2 over x to the first. That's one specific instance of that occurrence. Another example might be limit x goes to infinity of, let's say, 1 over x to the 1/2. Now we know that means square root of x, but that's still x to the 1/2. And so this is another specific instance of this occurrence. The theorem says this, that if we have r bigger than 0, that this limit is equal to 0. But let's see if we can sort of convince ourselves that is true. The idea is x is getting larger and larger. The question is, what is happening to that function value? Well, let's think of it this way. Suppose x is 1, well, that's 5. Suppose x is 100. We're choosing x getting very, very large. If x is 100, this is 5 over 100 to the third is 1 million. Is that right? Yeah. And so that's a very small value. 1,000, this would be 5 over 1,000 to the third power. And so that is what? What is that? 1 billion? Yeah. Yes. And so we can see that what happens as the x value gets larger and larger and larger, this quantity gets smaller and smaller and smaller. And it's not too hard to convince yourself that what happens is as x, the further out the axis x moves, the closer this function value gets to 0. And so that's our theorem. And that's true for any value of c, that's true of any value of r, again, assuming r is greater than 0. So this limit is equal to 0, this limit is equal to 0, this limit is equal to 0. Now, this is also true if you're approaching negative infinity, but we have one extra caveat. That would be true in this scenario, because 5 over negative 1 million is getting close to 0. 5 over negative 1 billion is getting closer to 0. So these values get closer to 0. That would still be true here. But this, in this scenario, this does not exist. The requirement is, this is true. As x goes to negative infinity, the same theorem holds. However, the function must be defined. You're not allowed to take square roots of negative numbers, and so this is undefined to begin with. So assuming that x to the r is defined, assuming the function is defined, it is also true if you're approaching negative infinity. And so if we have the limit as x approaches negative infinity, or as x goes to negative infinity of negative 2 over x, the same function, this is still equal to 0. The only time it would not be true is if the function is not defined as x values are negative.